Okay, I think we're gonna go ahead and get started. There might be stragglers coming in, but we'll just get going here this morning. So thank you everybody for attending one of the first workshops of the Alert Conference. My name is Xue Fan. I'm an application engineer at SonTek. I've met many of you already, but there are some new faces, so I'm looking forward to getting to know all of you this week. So thanks again for being here. This workshop is going to be primarily focused on ADCP users and those users who use ADCPs to do discharge measurements. It will be geared towards more of the intermediate user who has already had experience with ADCPs. So if you're a beginner user or have never been exposed to ADCP technology before, I won't actually be covering the basics or really defining any terminology or anything like that. But that being said, if you do have specific questions, feel free to interrupt at any time. This workshop is really for you guys, and any questions that you guys have, just please either interrupt during this workshop or find us afterwards. We do have a booth in the exhibit hall, so we have many people here who are experts in the field and who can definitely help you out. So with that being said, today's workshop is structured following a webinar that we did late last year. And the point of the webinar was really to address some of the common questions and concerns that we hear from users and customers. We wanted to provide you with field tips and solutions to basically be able to overcome some of the questions and issues that you'll see frequently in the field. So the 6 kind of topics or questions that I'm going to cover today include why choose a moving boat versus a stationary method for measuring using ADCPs. Number 2, why is an accurate transducer depth critical to your measurement? When and why do we do a compass calibration? Why choose one track reference over another? Why use vertical beam versus bottom track for depth? And then finally, is QRev required for post-processing? So with that being said, I mentioned that we do have many experts here in this room and at this conference this week. So along with myself here, we have Isaac Jones in the room. He's also an application engineer at SonTek. We have Matthew Klipfel. Do you want to raise your hand back? Matt is our Western sales representative, and so he has spent a lot of time with the USGS as well. So any sort of ADCP questions that you have, Matt's your guy. And then we have Tim Finnegan. You want to raise your hand, Tim? So Tim is a regional sales manager for our services and integration team. So anything to do with integrating our equipment into our remote boat solutions or buoys and platforms or anything like that, Tim would be the expert to talk to for those topics. And then finally, we have Ken Sim. Ken, you want to raise your hand in the back there? So Ken is the newest addition to our SonTek family. He is our velocity and flow lead for SonTek, and he is the new product manager for our ADCPs, including the RS5, which we have here today, and the M9, which many of you are familiar with. So that being said, please again find any of us during this conference if you have any questions, concerns, improvements to our products, things like that, bugs, suggestions, anything like that. We really want to hear from you guys. So please take this opportunity this week to grab us and talk to us. All right. So I did want to mention that we do have a training series, a video training series that we recently released. This has been a very long work in progress. This really covers the basics in how to take an ADCP measurement. It really goes step by step. There are at least 8 chapters here. There are a couple bonus modules as well. But if you have new people, new personnel who are unfamiliar with ADCPs, this is a great training series to show them. Make sure that they watch all these videos, understand really the basics, why we do things, how step by step how we do things. Before you take anyone out into the field, and this should give them a very solid foundation once you get to the field and actually take a measurement. So this is the link to the video series, and if you miss this in this presentation, we're happy to give you the link later on and show you where to find all of these videos online. And then finally, I did want to mention that we at SonTek pride ourselves in educating, and so every year we try to have some sort of large training event. And so this year is no exception. We have an event coming up later this year in October. This will take place in San Diego, and it's a multi-day event. And this will be geared towards the intermediate and more advanced users. It will be a kind of a 3-day intensive event where we'll have classroom sessions, group sessions, where we go through all the options that you have during a measurement, why you choose certain options. We'll go into the field and actually apply what we learn in the classroom to a fairly complicated site, where users will be able to make some of those choices for themselves and see how that changes their ultimate discharge values at the end of the day. We'll also be covering things, more advanced topics like velocity indexing. We'll be showing some high-pack bathymetry surveying techniques. And so it's kind of an all-encompassing training for those intermediate and advanced users if you have any of those folks who want to attend. So again, October this year. Pamphlets are on the tables here, so you can look up this event and look forward to seeing you there. All right, so let's just jump right into it. Any questions, first of all, before I move on? Can I just get a quick show of hands? How many of you are actually experienced ADCP users who use ADCPs for discharge measurements on the daily? 0. All right. Wonderful. How many of you have seen ADCPs or are familiar with ADCPs but might not use them? So John is, okay, good handful of you. Okay, great. So I'll try to tailor my talk to be able to make it at least understandable here for you guys. So the first topic, the first question that we hear frequently is why choose a moving boat versus a stationary measurement? So let me explain what that means. So going back to the basics, how we define a flow measurement. At the end of the day, we want a discharge value. So that's Q, or that's flow, or whatever you want to call it. Discharge is defined as a volume of water moving down a river or a stream or an irrigation canal per unit of time. So we define discharge as the cross-sectional area multiplied by the velocity. So Q equals V times A. All right, so in order to compute discharge, there are many tools and methods that people can use. We specialize in ADCPs. That's what we manufacture. So this is going to be purely the method using ADCPs here. So in order to compute discharge, our ADCPs will measure the velocity and the depth. So that's the actual measurement that we do. And then we use that information to calculate the discharge. So when we have an ADCP and we step across a transection in a river or a canal, we are actually, for every sample, taking these little slivers of areas. And for each little chunk, we measure a velocity within that area, and then we actually measure the depth, which then you can calculate that cross-sectional area of that little chunk. And the total sum of all those little chunks when you cross a river gives you that total discharge at the end of the day. All right, so there are two basic methods that are accepted and widely used for measuring discharge using ADCPs. The first is called moving boat on the left, and the second is stationary. So let's talk about moving boat first. The moving boat method is what it sounds like. It's basically you take your boat and you move it across the channel in kind of a smooth and controlled manner. When you do that, we are sampling continuously over this whole cross-section, and all these colors represent those velocity measurements that we see across the channel. So you see that we get a nice kind of uniform coverage depending on how the boat operator actually moves their boat, but generally speaking we get this nice broad coverage across that cross-section. So if you're following USGS guidelines, you will be taking multiple transects and averaging them. So if you imagine you take one transect, if you run into a situation where you have turbulence or an eddy or a pulse of something coming through, that's kind of an anomaly, and you want to take more transects just to be able to average those things out to get a proper mean channel velocity and mean channel discharge. So that's sort of the moving boat method. There's a little animation here. So in the moving boat method, we start at the starting edge, measure a velocity at that edge, and then move across. You see those nice colors here representing the velocities. And then you do an end edge here. You will see that there are some blank spaces. That blue here, we actually physically can't measure there, and so there are certain techniques that we use to fill in those gaps. So we use some extrapolations at the top and the bottom, and we do make some assumptions at the edges in order to cover that entire cross-sectional area. All right, so that was a moving boat method. The stationary, or what's commonly referred to as the midsection method here, is similar to, is anyone familiar with a weighting discharge measurement, like with a flow tracker or pygmy meters, AA? Okay, so this is the exact same method, basically, except that now instead of using a point velocity meter like a flow tracker, we are using an ADCP that measures the entire profile. So in this way, we actually get more information compared to just one point. And for those flow tracker users, if you wanted a multi-point measurement, if you're a little deeper and you need 2 or 3 points, that can take a while. And so with an ADCP, you're able to get the whole profile over the entire water column in just one sample. So with the stationary measurement, what you do is you kind of step through, you define these kind of concrete stations, and as you step through, you're going to be waiting at each station individually for, let's say if you're using USGS guidelines, about 40 seconds at each station. So you're physically stationary, not moving, and just measuring, and then you go to the next station and the next station. So stationary, this method is actually less widely used compared to the moving boat method. Generally speaking, it's because it takes a little bit longer because you are physically waiting there at every single station. Normally you want to cover about 20-ish, 22 to 25 stations across your entire channel. If you do have regions with very isolated strong flow, for example, you might want to even put more stations in there to really define how that central highest flow area is. And so it really kind of depends on your site. This can take a while. However, you don't have to go back and forth compared to that moving boat method. So you just do one transect across and then you're done. Yes?
So you're physically in the water with the unit with the stationary method?
It actually depends. So with an ADCP, we actually don't recommend that because one of the beams could accidentally hit you or whatever. So in an ADCP situation, people will be doing this, a tether or off a bridge or whatever you can figure out. There are also remote control boat options where there's like a loiter mode where you can just loiter and the GPS on the remote control boat will control that loitering situation. So this is kind of a brief animation of the stationary method. There's an option to actually add a GPS to the stationary method also. So you can do this manually with a tagline and just read off the locations as you go, but you can also use GPS to automatically read off those stations for you. So this is, again, just depicting that concrete station, measure, stop, station, measure, stop.
And the GPS will do the distance between the stations, and you can see it as you go. In real time in the software.
That's right. So those are the two general methods. So now you're probably wondering, well, when do I use one versus another? And I did mention before that the moving boat is generally a little bit quicker than a stationary measurement. So when you go to a site, many people kind of default to a moving boat situation, which is kind of to the left here. So when you have a site with good bottom tracking, good GPS data, no magnetic interference, kind of your ideal site, and you know that nothing's going to go wrong, you can use the moving boat method. That's going to be just fine. We see most frequently people when they want to use a stationary method is when they have sites with one or more complications. So this includes something like a moving bed. So if you are using, and I will define some of these terms in a little bit if these sound a bit unfamiliar to you. But if you are using a bottom track only system and you have a moving bed situation, oftentimes stationary is the way to go. So you don't need to track the bottom or anything like that. Stationary, because you know the location that you're at with the boat, you can get around the moving bed situation. Oftentimes a high sediment load, it helps you stationary because you're sitting there stationary and measuring and pinging continuously at the same location. And in that way you have a higher probability of getting good ensembles compared to the moving boat method where you kind of just zip through at any given point. And then if you have, say, no GPS available or magnetic interference, so magnetic interference includes stuff like if you're measuring off a bridge and your compass is going crazy, you might not be able to use the moving boat method, so you might have to default to stationary. With stationary, you can really kind of dial back all the different options and get really down to the basics, just the basic ADCP without any of the bells and whistles that we normally put in as options. So that's kind of the reason why you would use a stationary method in this case. So in the video series, we do focus on the moving boat method primarily, but there is a bonus chapter with the stationary method included. So if you are curious about how exactly to perform these measurements following these methods, then highly recommend that you check out some of these video series here. Okay, so moving on to the second topic here. Why is an accurate transducer depth critical for a measurement? So what is a transducer depth and what do we mean by that? The transducer depth is defined as that distance between the water line and the bottom of that central transducer here. So that's what we call, the vertical beam that's sitting in the middle here. And let's see if we can get our...
There's a blank slide button.
There's a what
I
button?
think there's a blank slide button.
Oh, there we go. Must have pushed it. So this is something that needs to physically be measured by the user and then input into the software so that we can make the correct calculations. So why is that important? So first of all, when we look at the total measurement, that total discharge, as I mentioned, is going to be the sum of all the separate discharges that you see here. So that's going to be that measured discharge where the colors are, and then those edges, and then the top, and that bottom section. So for that top discharge area, depending on where your ADCP sensor sits in the water, that area between the water line and that bottom part of the ADCP is actually physically unmeasured. So we need to be able to estimate how much that area is and then extrapolate the velocities into that area. So obviously if you enter in an incorrect transducer depth, that top area is going to be incorrect and then that top Q is going to be incorrect. So that's something to watch out for. But that transducer depth is also factored in when the ADCP physically pings down to the bottom and collects your depth measurement. So as you're going across, you're getting depth readings going across. If you enter an incorrect transducer depth here, that goes into your total depth measurement, and then your total area measurement is going to be off if that transducer depth is off as well. So those are the two factors to make sure, to basically keep in mind when you're actually entering that transducer depth. Make sure you enter it in correctly. So again, going back to that video series, throughout this presentation we're going to be referring to various chapters on the topics that I'm talking about here. So just a quick example of how that transducer depth can change depending on whether you enter in a value versus not. So this is just an example data set here where you can see that the transducer depth that was entered was 4 centimeters, and the total Q here, the average discharge is about 0.39 cubic meters per second, and that's a very small small Q here. But the point is that if we do remove that transducer depth, say we forgot to enter it in, we kept it as 0, which is the default value if you don't enter in anything, bringing that to 0, that Q went to 0.37. And while that's a tiny change, that percent change is 7.5%. So it's obviously site dependent, the amount of change that you're going to see if you have an incorrect transducer depth. If you have a shallow site, a big change in your transducer depth will give you a bigger change in your final Q. Or if you have a very wide site, that incorrect value in transducer depth will kind of propagate over a huge width. So at this site in particular, we had a 7.5% change. Another data example here, we have a little bit deeper of a transducer depth, 7.5 centimeters. So you can actually physically lower that ADCP when you have situations where you have turbulent water, bubbles near the surface. Oftentimes it's helpful to actually lower the instrument as much as you can to get it lower to overcome all those bubbles at the surface. So in this case, this is actually a measurement that Isaac had performed, and so he lowered it all the way, 7.5 centimeters. We have 38.8 cubic meters per second here. If we had a 0 transducer depth, then we actually have 34.98 here, which is almost a 10% difference just on this transducer depth alone. So if you're following USGS protocols, you're looking at between 5 to 10%, a Q value within 5 to 10% of your rating at a site. If you do not enter in transducer depth, you're already going to be, like for example, 10% off in this case. So that's something to really keep in mind, especially at sites like this where it actually does make a big difference. All right, if you want any more details on how we calculate transducer depth and more factors why we need to have an accurate transducer depth, we do have a technical paper here, so this is just a link to that if you are interested in looking into it a little bit more. Any questions so far on any of these topics? All right, so moving on. When and why do we do a compass calibration? All right, so all of our ADCPs will come with a magnetic compass. And there are situations where you actually do need to use that magnetic compass, but also situations where you don't necessarily need that magnetic compass. You'll notice that all of our ADCPs come with things kind of by default that will help in certain cases, but not all those things need to be used every single time when you do a measurement. It's really to kind of cover all your bases, to guarantee you that at the end of the day, when you come back, you have a proper measurement to add to your data set. So with a magnetic compass, when do we recommend that you do a compass calibration? Generally before each measurement. That's a great idea. You actually do need a valid compass calibration if you are using a GPS track, and I'll explain that a little bit in a little bit more detail in a bit. You do need a compass calibration if you're using a loop method moving bed test, and you do need a compass calibration when you're moving to a different site. If you change any configurations on the board, say you change a GPS system, change any of the sort of electronics, batteries, that sort of thing, you generally want to do a new compass calibration if you do that sort of thing. So what the compass calibration does is it basically calibrates to the environment and the magnetic field that we see around us. So when you're doing a compass calibration, you physically are going to be holding this and kind of dancing around with the board. You want to eliminate any sort of ferrous material that you have on you, anything that will create a magnetic field, including your phone, keys. Don't be near your work truck or any sort of like rebar or ferrous structures. So generally speaking, we want to calibrate the compass as close to that measurement transect as you possibly can get. So if you're measuring from a bridge, for example, you don't want to do a compass calibration on the bridge because your ADCP measurement is going to be downstream in the water away from the bridge. So when you do your compass calibration, the best practice would be to go down to the bank where you're actually going to do your measurement, do the calibration there, and get back on the bridge and do your measurement that way. So again, we do need that compass calibration if you're using GPS at all. And we do have parameters like a magnetic error that we report, so you can keep track of that when you're doing your measurement. That'll alert you to when your compass calibration is basically outside of any sort of interference. So there's quite a bit of error involved there. And then finally, you do need a compass calibration when you do a loop or moving bed test. And this is an example of what magnetic interference or magnetic error will look like. So this is a measurement done in San Diego. This is Mission Bay here, and the measurement cross-section was just right about here downstream of the bridge. And so I actually performed the compass calibration a little bit away from the bridge, right here in the middle of the water. And you'll see that as we moved across the bridge, we see these kind of hash marks when we get closer to the bridge structure here. And so you see this dotted line here, that's a 3.5% threshold that we use, and we generally say that anything above 3.5% error will start to interfere with your velocity measurements. So it's just something to keep in mind. The software will actually give you some indication that when you hit these values, just make sure to look at your data and make sure that they make sense as you move across your transect. Here's just another example. This is one of our test sites in Yuma, Arizona, where this is actually at a pumping station, and so there's quite a bit of infrastructure on either end and underneath here, and so all of these little hash marks that you see, this magnetic error goes up to like 12% here. This is almost, I think, was that 14%? So on either end here, we see that the magnetic error is quite high in this case. So these sites are problematic for situations where you're using a GPS, and so there are ways to overcome magnetic error, and I will go into a little bit of detail in some of the other topics here. Something else that has to do with the compass calibrations and heading is the magnetic declination. So that's actually a parameter that's very important to input, especially if you're using GPS and you're relying on that compass heading. So the magnetic declination, as most of you probably know, is just the difference between the true north and the magnetic north. And so that varies by location, and it varies in time. So it's something that you just want to keep in mind wherever you are and look it up if you don't know what that is. The effect of the magnetic declination or any sort of compass variation that you see is actually here. So the difference between the white and the yellow lines are when we have a magnetic declination of 0 versus the actual magnetic declination that we see at the site. And it's a small value, but you'll see that the yellow versus the white velocity vectors, these are pointing downstream here, you'll see that they're kind of crossing each other. And so one of these is correct and one of these is not correct. So you do have to look at your actual site, look at what the water is doing, make sure that these vectors are doing the right thing. If they're not, and you realize that you're next to a bridge or some sort of structure, you will have to keep in mind that maybe your compass is being interfered with, or that you didn't enter in some sort of magnetic declination that will bring those vectors to the right direction. Ultimately, when you do have vectors that are not going in the right direction, that's going to affect your ultimate flow, because you're going to be looking at all the velocities that are crossing your section here. So if they're crossing at an angle, then that's going to give you an incorrect velocity. All right. Just a tip here, there is an app called CrowdMag that's very popular. That's kind of the simplest way to get your magnetic declination wherever you are. So that's made by NOAA, I believe, and that's readily downloadable. So if you are in the field and you want to get a magnetic declination, this is a good way to do it. Give me time to write it down. Yeah, it generally does. Mm-hmm.
You can also just Google MagDec, and the NOAA website comes up. And if you have internet or data, you can allow location, and it'll just give you your local magnetic declination. You don't want to download that.
Yeah, that's good. Okay. So next topic that we hear often is why choose one track reference over another. Let me explain to you what that means. So having a track reference is essential during a moving boat measurement. So what do we mean by track reference? So the track reference is basically how the ADCP is moving across the transect. So again, that final Q value that we want is velocity times area, and we're really talking about that velocity parameter here in this case. So if you imagine you have an ADCP moving across, it doesn't know what it's doing, it's just going to measure whatever is underneath it. So it's going to include its own movement plus that water movement. And so at the end of the day, when we want to calculate Q, we want that water velocity only. So in order to do that, we have to take the ADCP measured velocity and subtract what we call the ship track velocity. So that's what we mean by a track reference. We need to know how the ADCP is moving to remove that from the data set so that we can just get to the water velocity. All right, so there are various ship track options that are available to you. In all of our SonTek ADCPs, we include what we call bottom track, and I'll explain to you what that means in a little bit. You will have an optional feature here to use GPS, so if you do end up getting a GPS option, then you will have another available ship track for you to use. There are kind of two flavors of GPS which come automatically, so you'll get both these options if you do have a GPS option, and we call that GGA and VTG, which I'll go into a little bit more detail in a bit. So when you're looking at the software here, you're going to see these various colors, and this is again automatic. You don't have to do anything special to get all of this stuff. Bottom track is going to be in that blue line here, for example, and then purple and yellow are those GPS tracks. All right, so what do we mean by bottom track? So bottom track is basically so in the same way that we ping into the water and we get those particles reflected off the water and we measure that water velocity, we can do the same thing to the bottom. So we ping off the bottom, calculate velocity of the bottom, and we use that information to calculate our ship track. So if you imagine, for example, you're sitting in the middle of a channel and the flow is moving, if you are stationary and you're not moving and the bottom is not moving either, you should have a 0 velocity if you're using bottom track. If your bottom starts moving, say if you have a moving bed situation, that's when you start to worry about your bottom track. So that's something to keep in mind when you're actually using your bottom track. Bottom track is, again, all ADCPs have bottom track automatically. You don't have to do anything special to activate that feature. It is highly accurate because it uses the same algorithm that we use for the water velocity, so it's going to give you the same accuracy. Another great thing about bottom track is that you can actually measure the water depths with the same pings. So the same way that we measure velocity off the bottom, we can just take an average of the transducer values that we use for these skew beams that we call them. We take an average depth using those values, so that gives us redundant depth compared to another depth measurement from the vertical beam. One nice benefit to using bottom track only is that you actually don't need a valid compass heading in order to get your final Q value. Your velocities might look a little bit different, but the math turns out that you actually don't need a valid compass heading. So if you're at a site where you have magnetic interference from a bridge, for example, for some reason you can't calibrate your compass properly, or you forgot to calibrate your compass, you can still get away with using bottom track. So some of the drawbacks for bottom track, I mentioned this earlier, a moving bed will interfere with your final discharge measurements if you have bottom track. So, so if you do have the ADCP and your bottom is moving downstream, even if you're stationary, your ADCP is going to think it's creeping upstream. And what that results in is an artificial low bias in your measurement. So if you do have a moving bed, there are ways to correct for that moving bed if you don't have GPS, and so we go into that a little bit in one of the chapters in the video series. And another drawback is that the bottom track samples are susceptible to errors when you're in sort of difficult situations, and that includes stuff like vegetation, high sedimentation, really variable bottom that can interfere with your signal. So just something to watch out for. And then if you choose not to use bottom track and you have a GPS option, you can always choose that. So when you start out doing a measurement and you choose one track reference or the other, you can also always change that choice in post-processing after the fact too. So you really need to worry about what you choose at the beginning of the measurement. You can always post-process that and change the track reference. So in that way, it's really nice to have a GPS system just as a kind of redundant backup, so that after you take your measurement, you realize that your bottom track didn't work out, you can default to GPS if you really want to. So just very briefly, those different GPS options that we have, I mentioned that there are two of them. One is called GGA, one is called VTG. So let's talk about GGA first. So GGA uses the lat and lon locations for ship track, so it's going to tell you where you are and look at the timing between the satellites to do that. One of the major drawbacks for GGA is that it is susceptible to multipathing. So what that means is that when you have tree cover or sort of high canyon walls or even tall buildings, that GPS signal might bounce off those obstacles before it comes to your receiver. And so that is going to look like these big purple spikes that you see in this transect. So that's something to watch out for if you are using GGA as your track reference. If you see multipathing happen, you might be able to use your VTG. These two options, again, are default automatic if you use a GPS option. So you don't need to manually pick which one to use. VTG uses the velocity. So it's a slightly different way of calculating the ship track compared to GGA. So it's going to use velocity very similar to how we calculate Doppler shift in our acoustics. And so while this is not susceptible to multipathing, it does have a requirement that you have to be moving. And generally, for example, USGS follows these guidelines that if it's 0.8 feet per second or 0.24 meters per second or less, then you start seeing some spikes and artifacts in your VTG signal. So you can imagine that if you're going close to the edge and you're waiting at the edge to take a measurement, you just want to look at your tracks and make sure that you don't see any big spikes or anything like that. Generally speaking, it's okay, but just to be aware of that when you're using your VTG. So for both of those GPS tracks, either of these tracks can be used when the bottom track cannot be used. So when you have bottom track issues, when you have moving bed, that sort of thing. And then it gives you a really valuable tool actually for troubleshooting, which I'll go into in a little bit. So as I mentioned before, with GPS, you actually require a compass heading because your GPS is going to tell you where you are, but it's not going to tell you how you're pointed. It's not going to tell you the heading. So you do need either to have a calibrated magnetic compass, or some users actually use a GPS compass if they have too much magnetic interference with a magnetic compass. And then, as we mentioned earlier, it does require a magnetic declination when you use your GPS. All right. So this is an example of one measurement. And when I mentioned that ship tracks here, when you have GPS as a redundant option, you can actually use that for quality control. So the SonTek ADCPs, again, will record all that ship track data during the measurement. And this is going to be independent and automatic. So you can actually change that ship track reference in post-processing if you need to. If you look at your measurement like this, the first thing that should stand out to you is that those tracks look very different. And so the first question you want to answer, especially before you leave your field site, is why? Why do these look so different? So let's look at the whole measurement here. On the left here, you see this quality control window. That's going to be a valuable tool for you when you're actually taking your measurement. You're going to start seeing warnings and errors. And you'll see here, I have highlighted here, invalid bottom track. So you have a couple invalid bottom track warnings here. That corresponds to the kind of row of black dots that you see here. What's happening here in this measurement is that we actually have invalid bottom track. And so this blue bottom track, ship track, actually looks way shorter than your GPS track and what the boat actually did, because we just have a whole bunch of invalid bottom track in the middle. So we just didn't make it as far as what we actually did in reality. So in this measurement, in this case, we definitely want to choose GPS as your ship track. If we chose bottom track, then we would get a lower Q value than what we expect, because that cross-sectional area is going to be shorter. So in this case, you definitely want to switch to GPS. So as long as you understand that you shouldn't use one reference and you should use another reference, then you're good to go. But in this case, you know, we had redundant track references, so you're able to switch between the two. So just to really quickly summarize GPS, I know there are a lot of options and this is a lot of information. The ship tracks, the bottom track is always included in these ADCPs. GPS is going to be optional. GPS does provide a redundant ship track reference, so that ensures the usability of your measurement, especially at the end of the day when you come back to your office and you realize that, for example, you had an issue with bottom track. You can always switch to GPS just in case. And then the quality control factor that you can play with. So again, just a reminder, for bottom track, watch out for moving bed. If you do have a moving bed, use GPS, or you can use corrections using a loop or a stationary moving bed test. These topics, if you want to learn more, are in that video series as well, or just come find us during this week. If you do use a GPS option, you make sure that you have a valid compass calibration. If you use GGA, watch out for your multipathing. If you use VTG, watch out for moving slower than that minimum speed that I mentioned. All right, any questions on GPS or anything like that before I move on? All right, how are we doing on time? Okay, so number 5, why use vertical beam versus bottom track for depth? I'll explain to you what that means also. So I mentioned earlier that our ADCPs measure depth, and that depth obviously comes into play in that cross-sectional area calculation that we need for their final Q. So the cross-sectional area is going to be defined as that total area, which is the measured area, that colored area, plus those edges. That measured area is going to be the depth multiplied by the width of the cross-section. And so our ADCPs will come default with 2 different types of depth references. We call that vertical beam and bottom track. So let's talk about the vertical beam first. The vertical beam is the central beam here. We also have, if you're familiar with our M9 ADCP, that bigger ADCP with the 9 transducers, there you will see a central beam here that points directly downwards and will calculate the depth directly underneath the instrument. So that's actually one of the benefits, is that you actually see the depth exactly where you're measuring at that time. However, because it's only a single beam, it is susceptible to jumps, especially when you have really variable bottom, like large boulders, artifacts, vegetation, and things that can really mess up the signal there. So it's something to watch out for if you're looking at vertical beams alone. And then the other option is the bottom track depth. So that's, as I mentioned earlier, that average among all the 4 beams. So that's going to give you an average over a certain footprint, depending on how deep you are. It's kind of the beam spread out a bit, but those 4 beams will give you an average depth that way. So it's not directly under the instrument, but it kind of gives you a surrounding average depth. The nice thing about an average is that it does often give you a smoother depth profile compared to your vertical beam in certain situations. However, the bottom track depth is susceptible to errors, especially when you're near vertical or very steep banks. I'll let you know what that looks like specifically. So this is back at that site in Yuma, Arizona that I showed you earlier, where it's just a kind of rectangular canal here. And so we have a vertical bank, and as you take your ADCP and move closer to that bank, if you have a vertical beam, you'll notice that the vertical beam is going to hit the bottom, and then you're just going to get close to the wall. If you have a skew beam, however, one of your skew beams is going to start hitting that wall before the others as you're getting closer and closer. And so in that way, because the bottom track depth is an average of all the skew beams, suddenly as you're getting closer and closer, you're going to see this red line here, your depth's creeping up less and less, more shallow as you get closer to the wall. And so if you look at that black line, which is the vertical beam depth, which kind of looks like reality, you know, we have the flat rectangular shape, versus that red line, the bottom track depth, which looks more triangular, and that's really not what's happening in real life. When you see a situation like this, you should again say, why are these two plots different? And you need to be able to explain to yourself while you're in the field why they're different, and then choose the correct option that is most close to reality. So obviously in this case you would be using the vertical beam depth for your reference and not your bottom track depth, because you'll be eliminating all of that area that you need for your cross section. Something to keep in mind for those M9 users, so this is our larger ADCP instrument, that central beam for the M9 is actually a lower frequency compared to all the other skew beams. So what that allows you to do is that while the skew beams will profile to 40 meters, the central beam actually goes to 80 meters. So that gets you deeper in situations where your bottom track range doesn't reach. And so this, for example, is actually a transect at the Amazon River, and we had some sections here where basically the bottom track depth cut out, but we still are able to use that vertical beam. And when you're able to do that, you can extrapolate those velocities, and you're still able to get your measurement even in depths where your vertical, your bottom track range has been exceeded. So it's just something to keep in mind for your deeper sites. So as I mentioned before, the M9 or the RS5, all our ADCPs will calculate both the vertical beam and bottom track depths automatically. You don't have to do anything special. We actually do automatically fill in gaps. So if you have one depth reference that has a hole, then the other depth reference will automatically fill in that hole if you do have a hole. So this is an example of that, where that black line is the vertical beam depth. There's a gap here, and that red line here is going to fill it in for you. And associated with this sample, you see that the bottom track is used as a depth reference. You get that warning. So the software is telling you, hey, I filled in with the other track reference because we're missing a sample here. You will also notice here that red line looks a bit smoother than the black line, so that's that averaging that we see. At this site it didn't really make a difference, but there will be some sites where you'll definitely see a big difference there. And then just a quick field tip for those users of the software. You can tell quickly what references you're using by looking at these icons in the software. So currently this is showing BT for bottom track, used as a ship track reference, and then that little blue circle there is the vertical beam, and so that means that you're using vertical beam as the depth reference. And then in post-processing you can change that, or in real time you can change that, and this is an example of what the icons will change to if, for example, you change to GGA instead of bottom track, and then the skew beams or bottom track beams for your depth reference compared to the vertical beam. So any questions before I move on to the final topic? Yes?
So an example where you had a vertical wall, and it was, the bottom track was not matching well with what was happening near the wall. But maybe bottom track was what you wanted to use for the rest. Is the reference you're using per ensemble, or is it for the whole transect?
Yeah, it's actually for the whole transect.
So you get to choose one or the other?
Yes, that's right.
Not sections where you want
That's
to.
right,
Okay.
yeah.
So in this case, you would have to select your vertical beam as your ship track.
Yes, that's correct. And if you do have situations where you need, for example, bottom track throughout the central section, this system and the software associated with this system has a tool that actually you can remove one of the beams from the calculation. And so you can actually physically remove this beam from the velocity calculation if you know that that's the one impacting the wall.
To correct for the wall.
Yeah,
So you still use your bottom
Yeah,
out
yeah.
certain beams.
That's right.
Okay.
Yeah.
And it might be worth mentioning the bottom track depth and not using the bottom track depth has nothing to do with your velocity measurement. Right. It's only for depth. Right. Even though it's bottom tracking for water velocity and then bottom tracking depth. If you choose vertical beam for depth, it has no impact on your measurement if you're using bottom track.
Yeah.
Yeah, that's one of my questions for like the next slide after this, like the difference between the bottom track and vertical beams, like, or maybe it's the next one after, yeah, where you have like a difference of like 0.5 meters between the two. Like that's, I'm not sure. I guess it depends on the organization or like what your goal is for accuracy. But I mean, so I guess what you're saying is like it's still going to be an accurate measurement, even though you have like that big of a difference in depth, because you just said it doesn't affect the velocity measurement. Or
Yeah, and actually, so it's kind of it's hard to see the big picture when you just look at an edge like this, for example. But what ends up happening is that, like if you have a slope, usually sites are more like this and not perfectly vertical. So if you have a slope and you're looking at the vertical beam, it's going to map out the slope for you. But if you're looking at the bottom track depths, you're getting an average, and so you're getting sort of lower numbers here and then deeper numbers here. And as you move along, that slope is going to be slightly different, but it's also going to be different on the other side as well compared to the vertical beam. And so actually the areas even out, if that makes sense. Yeah, it's you kind of have to see the whole picture.
Sure.
Yeah. Any other questions? Okay, this final topic might be a bit much for this audience, but anybody use QRev or familiar with QRev? Matt uses QRev. All right, so let me just mention here, in case you come across this, QRev is a tool specifically designed for the USGS. The USGS designed it and they use it in their post-processing of all ADCP measurements. And so this isn't our software, it's a USGS software, but many of our users are required to take our measurements into QRev. So that's why this topic is here. You're going to see more and more organizations adopting QRev just because the USGS really made a lot of effort to kind of normalize across the board all the different calculations and the different manufacturers of ADCPs in order to do things in the same way across the board. There are so many different calculations and pieces that go into a discharge measurement that every company does it differently. And so this is in an effort for USGS to really standardize the procedure. Now that doesn't necessarily mean that everything that they do is, well, I don't want to say correct, but it's there's really no correct answer. Some of the things, why don't I mention some of these things actually? That would probably make more sense. So this is just kind of, I know there's a lot of information that looks very confusing, but so some of these things like what we do, how we treat missing data. So for example, what we do, RSQ is the software we use with the RS5. And so for example, if we have missing data for a certain situation, like bottom track will hold the last 10 samples and then set the velocity to 0, whereas QRev will interpolate everything. So if you have a missing sample, it just fills in the gaps. So it's not necessarily wrong or incorrect, it's just a different way of doing it. And so they will, across the board, standardize linear interpolation, whereas, for example, if we have a GPS sample missing, then that sample actually isn't used, whereas the QRev will actually put some sort of linear interpolation in that gap for you.
And if it's a good measurement, you'll get the same thing from our software as QRev.
Very close, very close, yeah. But they actually go as far as to take the raw data, and we as manufacturers, we have certain filters and things where we look at kind of the really raw parameters and decide this is good or this is bad. And they actually kind of go into that as well. And so even if we do the exact same calculation, there'll be some samples where it'll be slightly different because of that. So, but at the end of the day, if you do end up using QRev, so they have automatic extrapolations, those blank areas that I mentioned earlier, they have automatic ways of doing that. And depending on what the software chooses for you, you might get a slightly different answer because you're extrapolating for those missing gaps there. So that's probably all I want to mention here. In the video series, you will see a section where we explain how to take our data and put it into QRev. So if you do end up having to do that, so the USGS actually physically has to, before they leave the site, they have to take our measurement from our software, put it into QRev, and make sure that it passes basically in QRev, yeah, before they leave the site. So something to keep in mind. Okay, I guess the takeaway message from all of this information is that really nothing beats real-time quality control. When you're at the field site, if there are things that you can do to improve your data, or you realize that your bottom track is missing, that you do need GPS, and you realize you haven't calibrated your compass, it's too late once you get into the office to realize that. You will have needed to do that in the field. So we do have, I mentioned this earlier, we do have this quality control window here, which is meant for the user to use in real time. It's actually, the warnings and the errors that you see here are the same errors that you'll see in QRev. So we made sure that we wanted to match what the USGS is using for their quality control. And so errors that are red like this are things that you really need to address in the field. Those are things that you can't post-process your way out of once you get into the office. And then those yellow warnings are warnings that you need to look at and decide for yourself when you're taking your measurement. Is that okay? Is that not okay? Can I get away with finishing up my measurement in these conditions, and do they make sense? So just some food for thought when you're taking your measurements. So that's all the kind of prepared material that I have for you today. So if we want, we can just open it up to general questions, feedback, anything you guys want to talk about, really. Yeah.
I have a few questions.
Mm-hmm.
First, on the stationary measurement technique,
Mm-hmm.
is the single software, I don't remember the QRS, is that the name of the software?
RSQ.
Does that handle that as well as the moving boat?
Yeah, that's a great question. So RSQ, that software platform, will have the moving boat method and stationary method embedded in the same software. If you're using the M9, which is our larger ADCP, it's a little bit of an older platform, and that actually has two separate softwares, but the same instrument, same idea. So, yeah. Mm-hmm.
And there's some post-processing that's built into RSQ, the newer software. It's not available in River Surveyor Live and River Surveyor Stationary Live, which are the M9 softwares. But after the measurement, you need to use River Surveyor Live or River Surveyor Stationary Live for an M9 measurement. But after the fact, you can open them in RSQ and do some of the post-processing that's available in there, and look at the data there.
And I've seen various ways of calibrating the compass. We have an agency that they have a tripod they set up that they set their ADCP on and then rotate it on that. And I've asked them about the metal and the tripod stuff. Would that produce issues in compass calibration, and would you know it if you were getting issues with calibrating your compass if there was metal?
Yeah, it could. It could. So first of all, that method we generally don't recommend for our ADCPs. The way that we need to calibrate our compass is to account for all the pitch and roll that you'll see in the field. And so most of the time people will have this and they'll physically go around and do this. There are other manufacturers with different compasses that actually require a really flat plane to calibrate on. So maybe that's what those users were doing. And I don't want to speak to their compasses, but for ours in particular, if you did do that, it would probably pass, and you will be accounting for whatever ferrous material is in your stand. So once you go out to the actual site and you're taking your measurement, you just want to keep an eye out for the magnetic error. Sometimes you can get away with it. I mean, if you're on a natural site with nothing nearby and you have very low magnetic error, and you just look at your velocities and make sure that GPS versus bottom track, those velocities are similar, it's really not going to make a huge difference. But that being said, there's always that risk if you do end up at sites where you do see magnetic interference, yeah.
Yeah, and if it passes the compass calibration, it doesn't necessarily mean it's good. If you pass the compass calibration, you put it in the water and start measuring, and then you see compass errors, that means it calibrated to that location on the tripod, and then now it's in a much different environment on the river, so that it's throwing up errors and there's an effect.
So you would know then at that point
It's significant.
that it's not
Yeah.
calibrated. Okay.
Yeah.
Well, in our
Or-
software,
Okay.
because we have compass alerts, errors.
Okay.
Just as a quick question, how many people in the room lead teams of people that go out and collect this type of data or work with other people to collect this type of data? Is that anyone?
That currently do it or will do it?
Will
We
or-
will do it.
Okay.
Great.
Work with
Yeah.
hydrologists.
I wonder if it might be interesting just to talk about like some of, and maybe Tim and Matt can help with this just a little bit, but maybe just to talk a little bit about why an ADCP is awesome. Like what's it gonna do for you, you know? And just kind of, you know, at the risk of being a little bit too salesy, but I think it could be good for this group a little bit. Do you have any thoughts, Matt?
Yeah, I think personally, I think it just saves a ton of time and you get a very accurate measurement. So accuracy and time in the field, if you're working in hot conditions, you know, a radiant discharge measurement or using a stationary method sometimes will take you an hour to hour and a half in 100-degree heat, whereas you can knock out a much more accurate measurement with a moving boat in 20-30 minutes and be gone. So I think the time savings overall is massive with ADCPs, and it's also just fun to play with boats. Get our remote control option. Play with remote controls all day in the water. Not a bad game.
Well,
And
there
you
was a-
came from the USGS, so you did it as an end user,
Yeah.
so you
Yeah.
can speak.
Absolutely. Yeah, I mean, when you're hitting multiple sites in a day, it's important to have speed versus quality, and that's really what ADCPs give you.
I work with a customer in Thousand Oaks who's new to this, and they're a little overwhelmed about flow tracker measurements, ADCP measurements. What's powerful about the RS5 is you can kind of use it for most use cases that they're in. And so they have a bridge there, and it's actually a really easy way for someone with very little hydrology experience to kind of cover most use cases to build out their rating curves. And so it's pretty exciting to have something that's so easy to use that you can give it to like a wastewater operator that can go out and take measurements over the course of the year.
And we talked a little bit about yesterday, there's a big safety factor too in not having to be in the water, which I think is kind of cool.
Absolutely.
Time savings involved in getting on waders or, you know, messing around with life preservers and all that kind of stuff too. But anyway, just a thought.
Yeah, that's great. Yeah, I think also just in terms of like technology and advancements in all of our systems across the board, it's been really cool to see all the new features and just the different options that everyone has, and the default options even are so, there's such a wide range of like use cases and things you can do with just a single ADCP instrument now. Yeah, it's very versatile.
And the user-friendly aspect of the software has improved with RSQ. We had somebody, like a 12-year-old was helping make some measurements, and she used our older software, which we think is still pretty good, pretty great. And then she switched over to the newer RSQ software. She's like, oh, this is so much better. It's so much easier to use. So that's
Yeah, on that note, it might really seem daunting with all the different verbiage and things going on, vertical beam, GPS. But when you actually kind of do a measurement a couple times, it really is user-friendly in post-processing. We also have a full team of support that you can call. You have technical support or any of your sales reps or anything like that. But it's not as daunting as it may seem to get out and collect a really good discharge measurement at a site.
You know, that's an interesting photo too. I just thought you might want to talk a little about what people are looking at, because it might be kind of.
Oh yeah, yeah. So around the world, including here in the U.S., there are these events that they call regattas, where they just kind of throw out as many ADCPs as they possibly can. Usually these are run by an agency, like here would be the USGS doing it, so they do it kind of regionally within their regional water science centers, and then this one in particular was in France, and so they kind of have the equivalent hydrology agency in France. And how many ADCPs did they have on the water?
We had almost 50 stations.
Yeah, yeah, it's just, yeah, all the way downstream, and they kind of do it like a competition where they're trying to get the closest Q to what they actually do, measure as a reference, and it really just kind of, number one, tests all the agency's equipment, so they want to make sure that everything's accurate, so that's how they can easily spot outliers and things that need to go back for repair and that sort of thing. But also they hone in on just everyone kind of standardizing their process and making sure that people are up to date on their techniques and the best practices and that sort of thing.
And it wasn't just SonTek, it was all ADCP.
Yeah, yeah, it's all manufacturers. Everyone shows up, and it's a good fun event. Mm-hmm. Yeah.
Do you find people are using these just for bathymetry? I mean, can you, like we have surveyors who
Mm-hmm.
they have to get a boat out, or they have to do that kind of thing. So
Yeah, yeah. So our larger ADCP, the M9, is primarily used for that purpose, although we are working to integrate the smaller one, the RS5, with HYPACK. I don't know if you're familiar with the HYPACK software, but that's our bathymetry surveying software. So yes, there's quite a bit of.
use it during the winter, during the storms, and then some of the surveyors could go out and use it to catch some bathymetry where
Mhm.
Savigny's channel bottoms.
Yep, absolutely. Yeah, the nice thing about doing bathymetry with an acoustic Doppler current profiler is that you actually have velocities as well. And so not only are you mapping out what the bottom looks like, but you can get like fluxes of stuff and flow. Yeah, so it's a nice all-encompassing tool.
So, with moving bed, do you do a loop test at the beginning to determine whether you have a moving bed condition?
Mm-hmm, yeah.
And
Mm-hmm.
can you correct the data based on that loop test
Yes.
without having to use the GPS?
Mm-hmm.
Okay.
Yes, you
Is
can do that.
all built into this RSQ software?
That's correct, yeah. You can do a loop measurement before or after or in between transects. You can do more than one loop moving bed test if you want, in case, like, you know, at the beginning of the measurement you didn't find a moving bed, but you kind of feel like there is a moving bed maybe towards the end of the measurement if flow conditions had changed. So you can do multiple. You can do a stationary moving bed, which is just sitting in the middle, versus that loop where you have to go back and forth. So any of those you can pick afterwards which moving bed test you want to use to apply the correction, and then you can pick which transects you want to apply to. So some of them you might not want to, depending on what your situation is. Yeah. Mm-hmm.
And you can compare that corrected version to the GPS version as well to see.
Yeah. So you can go flip back and forth. Let me show you. That's probably.
And it'll show you the original Q and then the corrected Q as well. So you can see, like, once you've applied the
Do I have this in?
loop correction, what difference it made in your final flow, final discharge.
But I have a screenshot here, maybe. Oh, no, this one doesn't have corrected Q. So if you do apply a moving bed test, this total Q, there'll be an extra column that says total corrected Q, and so you'll be able to compare the difference between no correction applied versus correction applied, and then you can toggle this between bottom track and your GPS to see the difference. Everything will be recalculated automatically once you toggle that.
And do you need HYPACK to get the bottom elevation out of it, or can you get the bottom elevation
You don't necessarily need it. Yeah, you can export all of this data, and the MATLAB export is what goes into QRev, and that's all the raw data. So you can manipulate that however you want. HiPAC just gives you kind of an easier way to visualize the data, the lat-lon, and then the actual soundings. But you know, if you have people or you who can process that manually.
Get a sense of what the bottom looks like, so you can put that in your other
Yep.
graphic.
Yep, you can do that pretty easily. Yeah, just
Yeah, you get all the depths and the lat long, so you can, you have another program that you want to use to map it.
Yep.
HiPAC's added value is just great visualization while you're collecting the data, and then you can create like bathymetric maps, calculate volumes. There's a lot of processing features, and you can remove bad samples, bad depth samples, which you can't do in our software. So you'd have to do manually if you're mapping it out in some other program.
Great. Well, if there are no more
One more
questions. Yeah,
question.
of course.
So the channels we have a lot of engineered concrete channels that move at pretty high velocities. Some of them upstream, they're woody areas so we have debris and basketballs from urban areas. And so explain how you use this, or maybe the bigger one, in, let's say, a 30-foot wide concrete channel that's moving, and it's got some, I don't know, might be supercritical flow. Does that work? I mean, it's so hard to do that, even dropping, one of those other meters, but I could just see something get snagged on that. So I just address that, because I know from a debris, this is great, because if it's deep, it'd be, obviously it's going to miss it, but you got the top, you got things bouncing around. So how does that work?
So generally, when you have situations like that, it is helpful to use a stationary method, just because then you're not required to do a smooth transect across. So if you got stuff coming down from upstream, then you can kind of avoid those by just picking your stations and not having to go across smoothly. If you do have stuff that's in the water, suspended, that's coming in the way of your actual measurements, you should be able to see that pop up. So we have this this profile plot here, and you'll be able to see these big spikes if there is interference. You'll get a whole bunch of warnings. The software might actually kick out those measurements and just not use them because they're just bad. So there's a lot of like QC going on behind the works here. So generally speaking, you should be okay, but just be aware and look out for artifacts and data that don't look right, because there will probably be some of those. Yeah.
And your exposure time can be less. So we say like you gotta move smoothly across, but you can still get a decent discharge measurement if you're moving across and then a tree's coming down and you move back to the side, or to move back towards the bank you started on, and then you continue on once the debris is passed. You can still get a decent measurement that way, kind of depending on conditions. And tomorrow at, I think it's 1:30, I'll be talking about a site where we measured in a, do you remember how wide Prado Dam's site is?
Oh gosh.
Compound concrete,
No, I don't.
or compound trapezoidal channel that's concrete, and it was moving.
Yeah. It's
And we
maybe
got
200 to 300 feet wide, a
200 to
couple
300
hundred feet wide. Yeah.
Moving at, what was it? It was like 10 feet per second.
Something. Yeah, 8 to 10, I think.
Yeah, and
Yeah, it was
we got
really
an okay measurement. It wasn't outstanding, but it was decent measurement.
Yeah.
That's it.
Yeah, but in general, if the boat's moving around or squirreling around, doing things, that's okay. The bottom track or the GPS will take care of it. This afternoon, we are planning to do some tests at the swinging bridge. So if you guys are on a field trip, I think you guys might be passing our site. So at the site, we were there yesterday, and there are some like boils just downstream of the bridge that kind of bring the instrument towards the bridge, almost underneath the bridge. And so the transect actually just looks like this big snaky pattern. But that's okay. The math actually takes care of it, and the GPS and the bottom track will take care of all those for you. So you're going to get the same answer whether you go across the river going like this versus just a nice solid line. So
You did dodge giant log.
I did, yes. Yes, so speaking of, that's what we did yesterday. Yeah. Yeah.
And
Yeah.
you guys will be out there today doing the same.
Yeah, we'll be out there too, so maybe we'll bump into you guys, whoever's on the field trip. Yeah.
Air is the enemy of the acoustics. So if there's a lot of air getting entrained, you'll, like Xue showed that SNR plot up there, you'll see like the beams spike way higher in the water column, and that's just because the acoustic frequencies we use don't propagate through air, and if it's anything more than tiny air bubbles, then it blocks the signal and it doesn't work.
Is today the only day you're going out doing that this week?
I think so, but you know, we can, if you guys wanted to do something specific, I mean, we're here, so
Okay.
we're happy to do whatever you guys need. Yeah.
Yeah, come talk to us.
Yeah.
After
Yep. All right, if there are no more questions, thanks again for attending, and look forward to talking to you guys more this week. All right, thank you.